Our focus in this chapter is going to be on solving systems of equations, but there's more than one way you can solve systems of equations. So in this first section, we're going to talk about how to solve systems of equations by graphing. Now, it's fair to ask, what are you talking about? What is a system of equations? Anytime you have two or more linear equations involving the same variables, they form a system of equations. Now they're just talking about the same variables because they're saying almost always would use x and y, but in science or other things you may sometimes also use like y and t. Well, you can't combine two equations or interact with two where one has an x value, one has a t value. So that's what that's getting at. So a system of equations really just means we're looking at more than one equation at a time, and we'll only be looking at two at a time, but in further math, you may have to look at 3 lines or 4 lines at a time. So a solution, so we're trying to solve these things, a solution to a system of equations is an ordered pair of numbers that satisfy or is true in both equations. So when you think about like when we graph, when we first learned that table method, we were finding different x, y values that go together that were on that line. So we're trying to find the x and y value that are on both lines. So first we got to learn some terminology. A system is called consistent if it has one or more solutions. That means it's consistent if the lines touch at least one point. It's inconsistent if it has no solutions. That's going to happen when we have two parallel lines, because they would never touch each other. Now, notice these next two terms we're going to learn only apply when we're talking about consistent systems. So really, it's like this is type 1, this is type 2, and you could call this type 1A and this type 1B. So 3 and 4 only apply when we're talking about consistent systems. In other words, these only apply when we have lines that actually do cross each other. So it's called independent if it consists of two different lines. And that's going to happen, or what will result when we have two different lines. It may not be shaped like this, but the point is they meet in exactly one place. So it looks something like this picture down here. Two different lines, they meet at one point. So that is a consistent and independent set. Independent because they're different from each other. They don't depend on each other. A consistent system is called dependent if it consists of two identical lines. So in that case, like you may have something like y equals 2x plus 3 and 2y equals 4x plus 6. And at first glance you're like, oh, well that's two different equations. But really it's the same equation. All they've done is multiply everything by 2 to get to this second equation. So in that case, even though they gave you two equations, it's really the same line. So they do meet. In fact, they meet at every point on their line. So remember it says one or more solutions. It turns out it's really one or infinite solutions because it'd be at every point on their line. So consistent or inconsistent, and then consistent gets split into two categories, independent and dependent. And I think these pictures do a pretty good job helping us see what's going on. So both of these two are consistent. It can be two different lines that meet in one point, or it can be two equations that are actually the same line, in which case they meet at every point on their line. And then the other category is inconsistent because it's two parallel lines that never meet. Okay, so now we're going to just look at this graph right here and see if we can identify how we should call these things, whether they're consistent or inconsistent, and if it's consistent, whether it's dependent or independent. So we're just looking at the graphs right now. They've already done the graphing for us, so we're just trying to look and identify. So in part A, it says we look at the line y equals negative x plus 2. So that's this line right here. And we look at y equals x plus 1, which is this line right here. So we're looking right now at these two lines, negative x plus 2 and x plus 1. So they match this category because they are two different lines that meet in exactly one point. So since they have a solution, they have a meeting point, that means they're consistent. So I would write consistent to describe them first. Now since they're consistent, I have to decide, well, is it independent or dependent? Since they're two different lines and they only meet in one point, that means it's independent. So we have two different lines that meet in one point. That means they are consistent because they have a solution, a point where they meet, and they're independent because they're two different lines. Now B is negative x plus 2, so it's still this one right here, and 3x plus 3y equals negative 3. So this time we're looking at this line and this line. Well, if you look, these two lines, which you call them line A and line B, they never touch. They appear to be parallel, so there's no solution to them. That puts them in this category. Since they never cross, there's no solution, and that makes them an inconsistent pair. And I don't have to think about whether they're independent or dependent, because those words only apply when we're dealing with consistent variables, or consistent system of equations. Okay, last one is C. We first look at 3x plus 3y equals negative 3. So that's the line that's been labeled as A right here. And also y equals negative x minus 1. That's line A right here as well. So that's actually the exact same line. If we rearranged it, we could make these equations identical. So when it's the same line, it's consistent because there is a solution. They do overlap. In fact, they overlap everywhere. But since they're the same line, they're called dependent. So those are the three scenarios we have. Consistent and independent when it's two different lines that meet in one point. Inconsistent when it's two parallel lines. And consistent and dependent is when it's actually the exact same line, just written two different ways. It doesn't even have to be written two different ways. It's just they write it as two equations, but it's the same line. Now this is something you just got to put to memory. I know we don't love memorizing things, but this really is just a simple matter of memorizing these two scenarios. Okay, so one method of solving a system of equations is to graph the equations on the same coordinate plane. The points where they intersect is the solution to the system. Or it could be R solutions, because if it's infinite, then there's more than one. Okay, so first step. When we want to graph equations, we talked about this in the previous lesson, the review of how to graph, we want it to be in slope-intercept form. So that means we have to get y by itself. So we'll do x plus y equals 2. And to get y by itself for this first equation, I'll need to subtract x from both sides. So I get y equals negative x plus 2. So let's just go ahead and graph that line, then we'll come back and deal with the second line. So we always start when we're graphing with the y-intercept, which is the constant, the number that's by itself. So that would be right here at 2. Then we look at the slope, which there's an understood 1 here. So this is a slope of negative 1, which we can write as a fraction by making negative 1 over positive 1. So starting at the y-intercept, this is telling us the slope. It's telling us to go down 1 first, and then over 1. And just to make sure we get these graphs as exact as we can, I would keep going down 1 over 1, down 1 over 1, down 1 over 1. You can even go up 1, left 1, up 1, left 1, just to help us get all the way across as exactly as we can. Now you don't have to label it, I'm just doing it to help make sure we are clear on what we're doing. That is the line y equals negative x, that's a negative there, plus 2. So now let's do the same work with this equation. X minus y equals 4. Our first step is to make sure it's in slope-intercept form. So I will subtract x from both sides, getting negative y equals negative x plus 4. But I can't leave a negative y, I need positive y right here. So I have to divide everything, all three terms, by negative 1. So that changes the sign of everything. Negative y divided by negative 1 is positive 1. Sorry, positive 1y. Negative x divided by negative 1 is positive 1x. 4 divided by negative 1 is negative 4. So the y-intercept is always where we start with the graph. So that's negative 4. So I'll go down 1, 2, 3. Negative 4 is right there. And my slope is the understood 1 in front of the x. So I can write that as a fraction by doing 1 over 1. And this is saying I go up 1 over 1, up 1 over 1, up 1 over 1, and so on. So now we know the solution is where the two of these meet, which is right here. So we can count over that's 1, 2, 3, and then down 1. So it's the point 3, negative 1. That is the solution to the system of equations because that's where both of these meet. Now you don't have to check this, but I want to show you how you can see this works. If you plug 3 in for x and negative 1 in for y, for both of these, you'll see it's true for both of them. Because we'd say 3 plus negative 1, and 3 plus negative 1 is 2. We'd say 3 minus negative 1, and we change that minus to negative to plus a positive, so 3 plus 1 is 4. So this point, this ordered pair, is true for both of these equations. It's also where their graphs meet, so it is the solution to the system of equations. Okay, like I said, the first thing we need to do is make sure it's in slope-intercept form. Now this first one is, so we can go and graph this one right away. Its y-intercept is 1, so I put a point at 1, and its slope is 2, which I can write as a fraction, 2 over 1. So that means starting at the y-intercept, go up 1, 2, and over 1. I can also go down 2 and left 1, down 2 and left 1, just to help make sure I get as straight a line as possible so I can find where the two of these meet. Okay, now this one is close to being in slope-intercept form, but we do need to get rid of that 2. So we've got to divide every single piece by 2, giving us y equals 2x plus 1. Hark, these are the same line. So I don't have to graph again because we've already drawn the line. So this is a situation where there are infinite solutions because these are the same line, so they overlap everywhere. It is literally the same line on top of itself, so they intersect everywhere. This is infinite solutions, and we would say it's consistent and dependent because they're the same line. Okay, number 3. The first one is already in slope-intercept form. Y equals negative 2. So we look at negative 2, and this means the slope is 0, so it's a horizontal line that passes through negative 2. This one we've got a little bit of work to do so we can get it in slope-intercept form. So I'll subtract 3x from both sides. then I can't have a negative y, so I have to divide all three pieces by -1, which makes everything positive, making it y equals 3x plus 1. So my y-intercept is plus 1, so I put a point at +1. My slope is 3, and I can write that as a fraction by writing 3 over 1. So I can go up 3 over 1, but that kind of gets me off the graph. So I can also go down 3 and left 1, down 3 and left 1 to get another point. So you can see that where they meet is at this point right here, which is -1, -2. So the solution to this system of equations is -2. Okay, number 4, this is a vertical line. Just like when you have y equals a number, it's horizontal. When you have x equals a number, it's vertical. So we go to +2 on the x-axis and draw a vertical line through that. Just have to do one step to make this to be in slope-intercept form, so I'll subtract 2x from both sides and get y equals -2x plus 1. So my y-intercept is +1, so I put a point there at +1. And I can write the slope as a fraction by making it -2 over 1. So I start at the y-intercept and I go down 2 over 1, down 2 over 1, down 2 over 1. So they meet at this point right here, which is at +2, down 1, 2, 3, so +2, -3. Okay, number 5. Got to do a little work to put these in slope-intercept form. First one, we just have one step. We just subtract 2x from both sides. We get y equals -2x plus 6. So my y-intercept for this one is +6, so it's right here. Then my slope is -2 over 1. So I go down 2, right 1, down 2, right 1, down 2, right 1, and so on. Okay, this will take us 2 steps to get it in slope-intercept form. We subtract 2x from both sides first. Gives us -y equals -2x minus 2. We can't leave the y negative, so we divide both sides by -1. So that turns everything to be positive, so it's y equals 2x plus 2. So the slope here, the y-intercept should be first. It's 2. The slope is +2 over 1, so I go up 2 over 1. And there we are, there's the intersection. So they intersect at this point, which is at 1, then we go up 1, 2, 3, 4. So it's at the point 1, 4. Okay, last one. Want to get y by itself? So on this top one, I'll need to subtract 3x from both sides, get 2y equals -3x plus 6. Then I divide everything by 2 to get y by itself. That gives me y equals -3/2 x plus 3. So this one has a y-intercept of +3. 1, 2, 3. And it's a slope of -3 over 2. So I go down 3, 1, 2, 3, and over 2. Down 3, 1, 2, 3, and over 2. Okay, on this one, we'll also subtract 3x from both sides. Then we'll divide everything by 2. So we get y equals -3/2 x minus 2, because 4 divided by 2 is 2. So this one has a slope of -2. A y-intercept of -2. So we put a point there. And then its slope is negative 3 over 2, so we go down 3 over 2. Okay, that doesn't work really well, so we'll go opposite. We'll go up 3, 1, 2, 3, and left 2. Up 3, 1, 2, 3, and left 2. And you may notice those two lines are parallel, which, if you look, we can see right there they have the same slope. So this has no solution. You can either write the words no solution, or you can just use this symbol. It's like a 0 with a diagonal line through it. That also means no solution. So there are 3 possibilities. You can see them all here. Some of them meet in one place, have one solution. Some of them are the exact same lines, they have infinite solutions. And some are 2 parallel lines that never meet, they have no solution.